Is there any adult-educated person on Earth who doesn't know about dinosaurs? The first thought would be, there is hardly anyone who has never heard about them. Indeed, we learn about them as children, when we barely start speaking. Cartoons, toys, drawings, and then movies, videos, articles, even ordinary ads. The ancient lizards are often shown in the most surprising places. As a result, the average city dweller knows more about dinosaurs than about a bird on a branch outside their window. Are there many who know what was before the dinosaurs? What animals lived 100 million years before them? Or what fearsome beasts lived 50 million years after them? We bet there are far fewer experts here. But there must have been some creatures living on the planet at those times, right? And some of those creatures were scarier than the dinosaurs, if not in size, then in appearance. Today, you're going to discover what ancient fish had a bite force twice stronger than a modern polar bear. What ancient bird had a wingspan almost as large as an F-16 fighter jet? What monster had the body of a bull and the head of a boar? And many more interesting things. Ancient animals scarier than dinosaurs. Dear viewers, please like and subscribe to our channel. It's easy to do, and it will help YouTube a lot. Your likes will help its algorithms to select interesting content and make it more accessible. According to one of the most compelling hypotheses, the first life on our planet appeared in the ocean. So we will start with the dwellers of the ancient ocean. The hero of the first story is Dunkleosteus, a predator that reigned in the depths of the Devonian seas 100 million years before the dinosaurs. The genus Dunkleostidae includes several species. We can talk not about all of them, so let's get to know the most formidable one, Dunkleosteus terrelli. Let's take a look at it. We have here an ancient fish with body, fins, and tail like those of fish living in the mid-water, not near the bottom. In biology, such fish are called pelagic. Pay attention to the head of the Dunkleosteus. An expert would immediately notice that it is not a plankton filter feeder or other consumer of marine minnows. The size and shape of the jaws clearly indicate it is a dangerous predator, hunter of large prey. But the most interesting thing is that these intimidating jaws do not have teeth, a toothless predator. It's hard to believe, but that's what it is. The sharp protrusions you see in the mouth of the Dunkleosteus are not teeth, but simply pointed edges of the jaw. Moreover, the shape of the jaw is such that the cutting edges are sharpened against each other when they clamp together. Not a bad design. After studying the mechanics and strength of the jaws of the Dunkleosteus, the scientists made two key conclusions. First, they found that the jaws could open so quickly that they sucked water in like a pump. This works well when hunting smaller prey. Second, they found that the Dunkleosteus had tremendous bite force. For example, calculations on a 6-meter-long Dunkleosteus showed a bite force of 4,400 Newton, 989 pounds at the lateral edges of the jaws, and 5,300 Newton, 1,200 pounds at the points of the central protrusions. For comparison, the bite force of a present-day polar bear is 2,570 Newton. That's half as much. A bit bewildering, isn't it? These weapons allowed the Dunkleosteus to easily deal with all but one prey. In a minute, you'll find out what this exception was and what role it played in the evolution of the Dunkleosteus. Now, let's find out its size, mass, and speed. The evidence at this point is contradictory, as the full skeleton of an adult predator has yet to be discovered. Some estimates put its length at 10 meters, 32 feet, and weight in the range of 3 to 4 tons. For the late Devonian seas, this was the largest hunter. For such a solid size, the Dunkleosteus was fairly fast. It could swim at a speed of 32 to 40 kilometers per hour, 20 to 25 miles per hour. That's a high speed for marine life of the Paleozoic era. As the largest and fastest predator, Dunkleosteus was at the top of the food chain. It preyed on amenities, sharks, plesioderms, and other Dunkleosteus. Yes, this is the very same exception prey we mentioned above. The fact of cannibalism is scientifically proven and allows for a very interesting hypothesis. Perhaps the brutal introspective competition served as one of the main tools for the evolution of the species. The worst enemies of the Dunkleosteus were actually its brethren, so its defenses improved in this direction. Note that in the 50 million years of the species' existence, it developed nothing to protect the back half of its body. It has remained open. Hence, we can assume that this part of the body was rarely attacked, and the defense there never appeared in the process of evolution. Apparently, the Dunkleosteus attacked the victim's head when it came to assaulting its brethren. It's a rational tactic. It hit the victim's most important organs without the risk of a return bite to its unprotected part of the body. Thus, in the course of evolution, those specimens with stronger defenses of the head, the front part of the back, and the abdomen gained an advantage. As a result, we see robust and tight-fitting armor protecting these parts. They greatly increased the chances of survival in case of lateral and frontal attacks by other Dunkleosteus. Of course, this is just a hypothesis, but it is quite plausible and recognized, and other alternatives are less convincing. For example, let's imagine that the Dunkleosteus preferred to attack from the tail. What would happen with this tactic? There are few options here. Most likely the attacked Dunkleosteus would try to wriggle out and bite the aggressor's tail. It's a very interesting sight. Two predators eating each other from the tail. Thus, attacking the tail of the rival, Dunkleosteus itself risks losing its tail. In any case, it would receive serious damage in response and most likely die. It is unlikely that such a method could have taken hold in the course of evolution. What else can we say about Dunkleosteus? Judging by the facts, it was the apex marine predator of its time and was in harmony with its environment. Accordingly, its extinction must have been associated with profound changes in that environment. The extinction of Dunkleosteus at the end of the Devonian is associated with two peaks in the global extinction process: the Kelwasser event, 372 million years ago, and the Hagenberg event at the Devonian Carboniferous boundary, 359 million years ago. According to current scientists, the Hagenberg event put an end to the diversity of marine species in the Devonian seas. There is no consensus on the causes of the extinction. Various hypotheses are suggested, including such exotic ones as supernova explosion or asteroid impact. Also, there is a hypothesis that the growth of forests, the movement of vegetation from coastal zones to the depths of the continent, resulted in a lack of oxygen in the water of Devonian coastal ecosystems. It is easy to imagine the objections of the opponents of this hypothesis. It is impossible, they would say. The more forests, the more oxygen in the atmosphere. It's really so, but the point of the hypothesis is the decrease of oxygen in the water, not in the atmosphere. There was less oxygen in the coastal waters due to the increased mass of decaying organic matter. This was the result of the forests growing deep inland. They changed the structure and composition of the soil, enriching it with organics. River flow changed accordingly. River water carried a lot of organics and other substances that stimulated the growth of microalgae into marine ecosystems. As they died and decayed, they took oxygen from the water. The lack of oxygen first led to the extinction of lower links of food chains, and then to the mass extinction of apex predators. In addition, sea currents may have changed during this period, and a large amount of hydrogen sulfide from deep waters entered coastal waters. The mystery of the extinction of Dunkleosteus is still waiting to be solved. Today, one thing is known for sure: a magnificent apex predator, perfectly adapted to natural conditions, completely disappeared from our planet. The hero of our next story, Doriaspis, also lived in the ocean depths of the early Devonian about 415 to 395 million years ago. Doriaspis was a jawless fish with an unusual body shape. Its remains were first discovered by Swedish phytopaleontologist Alfred Gabriel Nathorst during an expedition in 1882. 2 years later, the find was studied and described by British zoologist Edwin Ray Lancaster. He also gave the Doriaspis its first name, Scapeaspis nathorsti. In the 20th century, a British geologist, Errol Ivor White, began to study the curious fish. He completed the classification of the new species, and it had to be named somehow. White noticed that the outline of the fish looked like a combination of a spear and a shield. Taking the Greek names for these objects, he gave the ancient fish the name Doriaspis. Of course, we cannot say that this prehistoric fish was more terrifying than a dinosaur, at least because of its negligible size. According to available data, its length did not exceed 15 centimeters, 6 inches. Nor can we say today how dangerous it was, but it did look very intimidating. It had a strange body. The surface of the upper part of the body resembles a tortoise shell, and the belly is flat and smooth. The tail of the Doriaspis is long, flat, and thin, with spines on the edges. There are two long, almost round, bony protrusions extending from the sides of the body. In some species, the protrusions resembled fins or wings and had serrations along the edges. The purpose of these outgrowths is unknown. Perhaps they help the fish to float and balance in the midwater. However, their shape is far from that of a wing, so this hypothesis is not widely supported by paleobiologists. According to other versions, the lateral protrusions serve for species recognition and also as a specific tool for digging up silt. It is difficult to assess the plausibility of these options because it is still not clear what mode of life Doriospis had. It is not proven that this fish was pelagic, that is, lived in the midwater, but there is no evidence that it lived in the sediment area either. It is difficult to determine the function and purpose of any part of the body of an unusual fish unless we know how and where this fish lived and how and what it fed on. This is not good for science, but you can give free rein to your imagination. Try to suggest your own version of the purpose of the lateral protrusion. Who knows? Maybe your hypothesis will push science forward. By the way, in the case of Doriospis, this is not the only area for your hypothesis. The point is that the situation with the purpose of the central spike, or in scientific terms, rostrum, is not clearer. There is no unanimous opinion as to what Doriospis needed it for, or how it was used either. It is noteworthy that, unlike in the case of modern fishes, the spike is located under the mouth, and this is quite rational. The fish could throw up the bottom sediment with the spike. Thus, the fish immediately got all sorts of things thrown up from the body before its eyes and mouth. If there is something tasty, it could be quickly devoured. Remember that in the cruel world of natural selection, eating faster means being more efficient and having a better chance of survival. There is logic in such an explanation, but again it all comes down to the lack of data. What if Doriospis was actually a pelagic fish that lived not on the bottom, but in the midwater? Then the whole reasoning is useless. Unfortunately, there are far more questions than answers. We know too little about this strange fish. We believe that the main discoveries on Doriospis are yet to come. The subject of our next story is also partly connected with the evolution of life on Earth. In this story, we will present you not just one, as usual, but two ancient creatures, Mesosaurus and Mosasaurus. Their names are very similar, which sometimes leads to confusion, despite the fact that these predators were very different from each other. In addition to external differences, one of them is also famous for its special role in science. Further, you will learn which one of them has helped science and how. So let's talk about Mosasaurus. It was a very large sea predator. It is classified as a reptile from the order Squamata, family Mosasauridae, genus Mosasaurus. According to this classification, 5 species of Mosasaurus are known today. We describe the species Mosasaurus hoffmanni, and everything that will be further described about Mosasaurus is about it. Mosasaurus lived in the Cretaceous period of the Mesozoic era, about 145 to 66 million years ago. Fossilized traces of their existence have been found on all continents, including Antarctica. They inhabited warm, shallow seas that were widespread in the late Cretaceous. These ancient sea lizards were warm-blooded, viviparous, with a high metabolic rate. An adult Mosasaurus could exceed 10 meters, 32 feet in length, and weighed up to 70 tons. Their average lifespan was about 42 years. Mosasaurus fed on bony fish, cephalopods, sharks, and marine reptiles. Sea turtles were its main prey. In the last 20 million years of the Cretaceous period, Mosasaurus drove out all their competitors represented by large mackerel sharks, the last pliosaurs, and earned the title of the top sea predator of their time. Mosasaurs became extinct about 66 million years ago, along with dinosaurs and petrosaurs in a mass extinction at the end of the Cretaceous period. As apex predators, they significantly influenced the evolution of many sea animal species. Notably, the evolution of Mosasaurus gives us useful information about another interesting process. We know that the ancestors of the Mosasaurs lived on land, so the evolution of this predator helps us understand how the transition of a reptile group to an aquatic habitat occurred. Now let's talk about Mesosaurus. Mesosaurus fossilized remains have been found in early Permian sediments. These sediments were formed 299 to 271 million years ago, so scientists believe that Mesosaurus lived in this period. It had neither impressive size nor weight. It was only about a meter, 3.3 feet long, and it fed on small crustaceans and other minnows. A seemingly unremarkable, humble saurian, but it played an important role in the history of Earth science. An important fact was that Mesosaurus lived in fresh water. It could not stay long in salt water, respectively, it could not cross the ocean. Another important point, Mesosaurus appeared almost simultaneously in South Africa and South America. The German meteorologist Alfred Wegener drew attention to these details. Knowing that Mesosaurus could not cross the ocean, Wegener decided that Africa and South America were once a single whole. On this basis, he proposed a theory of the continent's origin as a result of the splitting of an early supercontinent to several parts. Wegener published his hypothesis in 1912. Later, this idea, after thorough revision, turned into the modern theory of tectonic plate movement. This is how Mesosaurus from ancient times influenced modern science in a very unexpected area. This is its role in science, which we promised to tell you about. You have to admit, we have a lot to commend the humble freshwater lizard for. Now, let's move from the ocean to land and get to know amazing and fearsome creatures that lived after the dinosaurs. In the late 1880s, paleontologists Carlos Ciriaco Amenguino and Francisco Pascaccio Moreno reported to the world the existence of Phorusrhocidae, ancient flightless birds. This fact led to the realization that the entire history of flightless birds is like an iceberg. The few species that live now are just the tip. Most of this iceberg is hidden in the past, and part of the hidden history was the giant Phorusrhocos, which appeared in the Paleogene after the extinction of the dinosaurs. In total, there are about 20 known species of them. Phorusrhocos roamed South America about 62 million years ago, until the mid-Pleistocene about 1.3 million years ago. An adult Phorusrhocos reached 2.5 meters, about 8 feet in height, and weighed 150 kilograms, 330 pounds on average. It had a large head and a bulky beak flattened on the sides. The end of the beak had the shape of a large hook. The ancient bird leaned on powerful legs with large claws on its toes. These details unambiguously indicate the predatory mode of life of these birds. Thanks to their long, muscular legs, Phorusrhocos were able to stalk and chase their prey long and efficiently. They were key predators in South America during its long geographic isolation. About 2.7 million years ago, North and South America united. The faunas of the continents began to blend, and the Phorusrhocos gained competitors. The invaders were stronger, so the local predators lost to them, and gradually became extinct. One of the Phorusrhocos, Titan's wallaby, tried to escape. This species made it to North America on foot, but even there a cruel fate befell it. The remains of this species were found in the south of the USA. Today, Phorusrhocos is of interest not only as a bird that lived millions of years ago. This species is of great value as a result of development in isolation. One must agree that a bird that abandoned flying is an interesting evolutionary experiment. There are still debates about the reasons for this, and they may have a very interesting conclusion. The fact is that natural selection plays a major role in evolution. In a highly simplified form, it works as follows. Features that are useful for survival and reproduction are strengthened, while harmful ones eventually disappear along with their bearers. They simply die out. The main mechanism here is random mutations, due to which features appear or disappear, and natural selection only reinforces the successful version. The role of natural selection in evolution is well known, so the question is, what was wrong with Phorusrhocos? We know for sure that it had no competitors, which would have caused it to give up flying. So why did its wings diminish greatly in the course of evolution? Why did it stop flying? It wasn't easy to find a reason, but it was found. It has to do with the behavior of these huge birds. They didn't need to fly to find food, to reproduce effectively. They didn't want to fly just to admire the terrain from above. Flying may be a pleasant activity, but it is very energy-consuming and potentially risky. The last two arguments were decisive and gradually led to the Phorusrhocos to give up flying completely. The wings of the Phorusrhocos remained, but gradually shrank to a size useful in an exclusively terrestrial life. Natural selection, of course, did not disappear. It helped the flightless bird to get powerful legs and other features that allowed it to excel without flying. Parasaurus became extinct around the middle of the Pleistocene about 1.3 million years ago. Their closest present-day relatives are sirenias, two species of land birds of prey in South America. Their long, slim legs are only a faint echo of the former glory of their mighty ancestor. The biography of Parasaurus tells us that after the dinosaurs, the birds managed to adapt to a purely terrestrial life, and there were even territories where they ranked as the dominant predators. This is certainly an amazing transformation, but you're probably wondering, what happened to the sky? Did all descended to the ground, and the sky stayed empty after the pterodactyls became extinct? Now, you'll learn who got the reins of the sky after the flying lizards. Meet Argentavis. According to modern data, Argentavis lived in the territory of modern Argentina during the Miocene epoch, about 23 to 5.3 million years ago. This means that in terms of time and place, its biography overlaps with the biography of the hero of our previous story, Parasaurus. Argentavis was about twice the size of the largest flying bird of today, the Andean condor. Argentavis had a wingspan of about 7 meters, which is only 3 meters less than that of the famous F-16 fighter. In terms of size, it could have rivaled the Pterosaurus, but those had died out long before its appearance. Argentavis weighed between 70 and 72 kilograms, 154 and 159 pounds. The height or distance from the ground to the top of the standing bird reached 180 centimeters, 6 feet. Just imagine yourself next to such a birdie. You've probably started to wonder how such a giant even took off. How high and how long could it fly? Research in this area has led to interesting conclusions. It turns out that the pectoral muscles, and this is the main power machine of flight, of Argentavis were smaller than those of other flying birds in percentage terms. This means only one thing. Argentavis could not stay in the air for long, continuous flapping its huge wings. Most likely, Argentavis relied on air currents and flapped its wings only during the takeoff and landing phases. Thus, the large wings helped it to stay in the sky as long as necessary, relying on the rising air currents. In addition, such wings made it possible not only to soar in the sky, but also to fly effortlessly in any direction. To do this, Argentavis gained altitude in the rising currents and then glided down in the desired direction. As a result, Argentavis could fly long distances with almost no wasted energy. This is an extremely energy-efficient type of flight that is used by glider pilots today. Takeoff was the most difficult task, as its huge wings inevitably touched the ground as it flapped. It probably relied on air currents here as well. It could run towards the wind so that lift force was generated and then use its strong legs to jump up into the air. Argentavis might also have used a jump from the top of some hill to take off. Now it's time to understand why it flew. I hope none of you have been confused by this question. Apparently, it flew to get food, and scientists have found out what kind of prey it was looking for. It is recognized that Argentavis was carnivorous, but it was not an active predator. That is, it did not attack and kill. It had an inappropriate body shape and relatively weak pectoral muscles for this purpose. The most likely behavior for Argentavis was that of a scavenger. The life of a scavenger is much more relaxed, and success there is achieved through fewer energy waste. As for competitors, they were small mammalian scavengers unable to confront Argentavis due to its size. It is not difficult to answer the question of who provided it with prey. Let's just remember that the main predators of Miocene South America were flightless birds, Parasaurus, which we have just described. They could easily destroy large prey, and perhaps it was these predators that provided the large amounts of carrion that helped Argentavis to survive. It only needed between 2.5 and 5 kilograms, 5.5 to 11 pounds of meat each day. For its size, that's a relatively small amount. So what do we have in the end? Argentavis had no threats in the air. It could hover safely for hours and wait for its flightless counterpart to leave him something for lunch. And it was satisfied with little, thanks to its amazing energy efficiency. Low food consumption and special mode of hunting of Argentavis led paleontologists to the hypothesis that this bird was also relatively long-lived. It is now believed that its lifespan amounted to at least several decades. Thus, Argentavis survived, according to the so-called K strategy. Let's explain a little bit what that is. The K strategy is living within the boundaries of one's ecosystem without changing numbers. The number of specimens is determined by the food reserves in the ecosystem. With this strategy, a small, stable population of scavengers has a good chance of survival. Argentivus laid 1 or 2 eggs every 2 years, so it had few nestlings. According to the K strategy, they stayed with their parents until they learned to find food on their own. With this reproductive rate, the number of other species did not increase, but neither did it decrease, since Argentivus died mostly from old age and diseases. Other causes accounted for no more than 2% of the death rate. Although Argentivus was undoubtedly a successful predator, this did not save the species from extinction. It did not survive to the Pliocene, and today, only fossils of millions of years old prove its existence. At this point, we finished talking about flying and non-flying prehistoric birds. It's time to move on to the most interesting animals after the dinosaurs, the mammals. One of the most interesting ones is Platybelodon. It belongs to the genus of Gomphotherium, extinct proboscidean, relatives of modern elephants. They lived in Africa, Eurasia, and North America during the Miocene and Pliocene eras more than 15 million years ago. In the Pleistocene epoch, after the merger of North and South America, the faunas of the continents mixed, and the Great American Interchange took place. And so, Gomphotherium got to South America as well. The only territories they couldn't reach were Australia and Antarctica. Gomphotherium reached the peak of its diversity in the late Miocene and became extinct in the Pleistocene. Externally, the Platybelodon looked very much like an elephant. It had 2 upper and 2 lower tusks, but unlike modern elephants, its upper tusks were bent downwards. Science doesn't know the reason for this, although there must be a reason. We know that evolution doesn't tolerate useless things. However, the upper tusks are not the most interesting thing about Platybelodon. These bizarre mammals became known for their 2 tusks on the lower jaw. They were without enamel, broad, and flattened horizontally, which gave them a resemblance to the blade of a bayonet shovel. In 1936, when describing Asian specimens of the genus Platybelodon, the famous paleontologist Henry Fairfield Osborn was the first to compare the lower pair of tusks to a coal shovel. The comparison became firmly rooted, and Platybelodon has since been often referred to as a shovel-tusked Gomphotherium. Today, of all the proboscideans, Gomphotherium still remains the most popular object of study for paleontologists. The main mystery of Platybelodon is the purpose of the shovel-shaped armament of the lower jaw. Presumably, it has something to do with feeding, but it is not known exactly how it was used. Accordingly, it is not clear what the Platybelodon fed on. It was assumed that the lower tusks were used as a shovel for digging and raking plants. There was also a version of cutting leaves off branches from trees. Another hypothesis was raking algae from the bottom of the freshwater lakes. There was also an opposite conclusion. Platybelodon did not use its bone shovels at all when eating. But the hypothesis of a shovel for algae was supported by a lot of scientists. Specific wear, which was explained by the abrasive effect of sand and clay on the shoals, supported him. This is how he was drawn everywhere, digging in aquatic and coastal vegetation. After this hypothesis, it would seem everything calmed down, disputes quieted. But in 1992, the scientific world was shaken up by the work of paleontologist David Lambert. According to the results of the study with the use of modeling, he concluded the lower jaw cut bark and branches. Later, having examined the microlayer of the surface of the tusk shovels, the Chinese scientist came to the same conclusion. Moreover, they noted that adult Platybelodons ate coarser food. Well, it looks like it's time to depict Platybelodons at lunch in a dense tropical forest, although we cannot say for sure that the search for the truth has come to an end. Finally, we invite you to learn about the fascinating discovery story of another predator that lived in Central Asia during the mid and late Eocene epoch, about 45 to 36 million years ago. The world learned about Andrewsarchus from a skull discovered in Mongolia. It was found by an expedition led by the American scientist, paleontologist Roy Chapman Andrews in Inner Mongolia in 1923. The skull was found in the Erden-Manga sediments formed at the end of the mid-Eocene. At first it was thought that the skull belonged to a giant suiforms from the Entelodonte group. These are extinct mammalian predators with a body resembling a bull and a head resembling a boar. We immediately recall the ancient Greek myths about the Minotaur, right? However, this hypothesis didn't last long. A year later, the above-mentioned paleontologist Henry Fairfield Osborn determined the found skull belonged to a predator from the family Mesoneichidae. He also described the new predator and named it Andrewsarchus in honor of Roy Andrews, the head of the expedition that found the skull. When reconstructing Andrewsarchus, it was found that its body length was 3.8 to 4.5 meters, 12.5 to 13.1 feet, and its tail was 1.5 meters, 5 feet long. The weight of this ancient predator could have exceeded a ton, 2,200 pounds, considering that it had a skull 83 centimeters, 2.7 feet long, and 56 centimeters, 0.85 feet wide. We can consider Andrewsarchus the largest terrestrial carnivorous mammal that ever lived. There is something mystical about the look of the Andrewsarchus. Look at this beast. What does it remind you of? Think of horror movies about werewolves. There is a certain resemblance, right? It is safe to say that in terms of frightening appearance, it was a worthy heir to the Tyrannosaurus. There is one unpleasant thing about the story of Andrewsarchus. Almost 100 years have passed since the skull was found, but nothing else has ever been discovered. Excavations are continuing all over the world, but there are no more skulls, let alone a whole skeleton. It's pretty strange and brings up some thoughts. Maybe there was no such species. Maybe it was the skull of some anomalous Mesoneichidae, another extinct mammal, which is far less mysterious. Of course, this can't be a final conclusion. But not a single bone in 100 years? There is definitely plenty of food for thought.